This one is number 8 handout of the connectivity, and it is talking about the structure of a 3-connected graph. And before moving on to the structure, we want to introduce a new operation. It's called a contraction. Contraction is the noun, and the contract is the verb. So basically, the meaning is, I have an edge. It must be an edge, okay? U and V are adjacent, and U itself has some neighbors. V itself also have some neighbors, and of course they overlap, possibly overlap. So one side is the neighbor of U, the other side is the neighbor of V. Well, technically it is the neighbor of U and take out the V, and the neighbor of V take out the neighbor of take out the vertex U, right? The contraction is saying that now try to make the two vertices together, and we call that W, whatever you want to call it, okay? Two vertices becomes one vertex, and it preserves all the possible neighbors. So if you look at U and V, all the vertices that it goes to is all the vertices that is in the neighbor of U or neighbor of V, and it is not U or V. And you draw an edge from W to all the previous neighbors. So it will be easier to look at a concrete example. U and V on C5. Okay, we got 5 vertices as a cycle, and U and V are is an edge. U and V are adjacent. So you can combine the U and V, and we call that as W. Preserve all the remaining vertices, but U is adjacent to one vertex below, V is adjacent to the other vertex below. So this means that W is adjacent to 2 vertices here. And so the contraction of C5 is equal to C4. So emphasize again that UV must be an edge. To do so. And in fact, if we call this graph as G, well, C5, then the contraction is called C5, like quotient UV. This is the notation. We say G quotient an edge means the contraction. One more example is this K4. Okay, in K4 you still have any edge U and V, and whenever you do the contraction, you realize that U goes to 2 vertices below, and V goes to the same vertices below. And so when you are doing the contraction, just add one edge to these 2 vertices. So you will see that such an operation kind of preserve how the graph look like. It was a cycle, then it is a cycle again after the contraction. It was a click, and after that it is again a click. So contraction is something that basically preserves the structure, although what is the structure is not so clear. It's not well defined, but you kind of can tell that the contraction preserves the topology of the graph. Okay. Okay, one more thing. Whenever you are doing a contraction, the number of vertices will decrease by 1. So it keeps dropping down. The graph has become smaller and smaller. So later on, we are going to say that every 3 connected graph, you can find an edge and apply the contraction so that it is still 3 connected. And you can find another edge again and do the contraction again. And keep doing the contraction until it becomes the smallest one. But if you think of the smallest graph that is 3 connected, then it is the K4. Okay? Actually, this one is the smallest 3 connected graph. If you do anything further, if you do the contraction again or take out any one edge from there, take out one vertex from there, then it is no more 3 connected. So K4 is the smallest building block for 3 connected graph. And now we're going to describe the theorem. It's lemma 3.2.4 in the textbook. It says that every 3 connected graph, you can find an edge, and by doing the contraction, it is still 3 connected. But the requirement is that G cannot be K4. K4 is the smallest one. You cannot do any further than that. Okay, so I believe the statement is easy, and now let's try to look at some pictures, examples, so that we can have a better image in our mind. Okay, if you draw the graph on the left, and you can try to just check by definition that this graph is 3 connected. Taking out any 2 vertices, it's okay. It does not break the graph apart. Now you can try to find some edges. Okay, for example, I can take this edge in the middle as E, and I call the other edge as F. Okay, so you have 2 options. Let's call this as G. If you do the contraction with F, then the graph becomes this. The 2 endpoints of F will merge together, and suddenly it seems this structure is not so well, and particularly this is no more 3 connected. Even though G itself is 3 connected. So you see the statement of this theorem. This theorem says there is an edge. It does not tell you that you can do this on every edge. If you apply the contraction on F, then you get the trouble. But if you do it on E, then it is no problem. Okay, so if we call this as edge, then you see edge is a 3 connected graph again. So you can pick one edge. And now you see the example, you have to pick the edge wisely. If you pick a wrong edge, say if you pick an F, then it doesn't work. I'm not going to do that again, but if you pick the edge wisely, then you found an edge, and then you can do edge contraction with E, then it becomes K4. And done, because K4 does not satisfy the requirement of this theorem. We have to stop at K4. But before we reach in K4, every 3 connected graph we can find an edge and keep making it smaller and smaller. So it's an interesting situation that it does not tell you that every edge can do so. You have to find a particular edge. And about how to find such an edge, then you have to read the proof. Okay, this one is not so easy, but the proof is not very long either. So take some time to read the proof. If you have any question, you can let me know. Okay, so if you look at this and you see, okay, it is great. Every 3 connected graph can be obtained by this way, and so maybe every 3 connected graph you can construct from K4 and do the opposite way, right? K4 and we call that decontract. Do the decontraction, the opposite of contraction, and do the decontraction, and keep going up, and then you can make it work. But it does not always the case. Okay. If after the contraction, let me draw it here. You see 3 connected graph, do the contraction, it is 3 connected graph. How about the opposite? If you have a contraction which is 3 connected graph, can you guarantee that the original graph is also 3 connected graph? So get the meaning? G is 3 connected, then contraction is 3 connected. But now the contraction is 3 connected. Does that mean that G itself is 3 connected? So here is a question. If G contraction is 3 connected, is G itself 3 connected? Okay, and this is a reasonable question. But if you play with that just 2 or 3 minutes, then you will realize that it's a super easy question. Okay, so let me show you an example. This is G, this is E, and after the contraction, this is contraction, it is K4. And after the contraction, it becomes 3 connected. But previously, it wasn't 3 connected. So this means that you cannot naively just try to decontract one edge to make it into, to add one more edge, one more vertex inside, because they will cause some trouble. It might not be 3 connected again. But the trouble is, you will see that here is the cut vertex. It's because this vertex has degree 2. This guy has degree 2. So degree 2 automatically guarantee the connectivity is below 2. This is the trouble. So actually there is a theorem that make both direction more complete. So this is the theorem 3.25. It says that a graph is 3 connected if and only if there is decomposition such that the same happens again. G1 is the building block, but now G1 is equal to K4. And GK, the last one, has to be G itself. The important thing is the building step. GI has an edge. We call the XY, such that basically the contraction is equal to the previous graph, such that GI is equal to GI plus 1 doing the contraction. But more than that, the degree of X and the degree of Y, both of them are at least 3. So here is the key points.